Okay, we're back again. This time we're going to look at some other simple machines that are still in the same family of machines as the lever. Other simple machines in the lever family. That's what we'll call them. And the reason they're all in the same family is because they all sort of work on the same principle. So, we start off, of course, with our lever. We've done the lever enough that we understand how that works. Your effort force and your load force. And, of course, the distance, or the length of the load arm, which we call RL, and the length of the effort arm, E. And we saw that with the lever, you can calculate mechanical advantages, right? The IMA, the mechanical advantage for the lever, is the ratio of the arms, the effort arm length over the load arm length, right? And the actual mechanical advantage, we said, was a little bit different because you would lose some force. So when you do the actual mechanical advantage, you use the forces. When you take the force of the load or the weight or whatever it is, and you compare that to the effort force, and you'll usually find that because there's some wasted energy or wasted force, the effort force is a little bit more than it needs to be in order to just lift the object. So the AMA is always less than the IMA. All right, let's look at another kind of machine, which is sort of like a lever, and it still has the same idea where we're trading distance for force. Remember how I wrote that in the last video. So I'm going to try and draw a picture now of what we would call a wheel and axle. Or, in fact, it kind of looks like two wheels sort of all joined together. So what I'm going to draw here in blue is a small wheel. And then on the same wheel, we'll have a larger wheel. So these are both joined together, and they all turn at the same rate. It's part of the same thing. It's kind of like if you think about cutting through the axle of your car, the part in the middle would be the axle, and the part on the outside would be sort of the wheel, I guess you could say. But instead of the wheel turning around the axle, we want the axle to turn with the wheel. So here's how it works. If you take a heavy object, say, like this, there it is, there's our load, all right, and we attach that with a rope to the smaller of the two wheels. We're going to attach it to the little wheel, which is actually the axle in the middle. Okay? So let's attach it to the axle in the middle. Let me see how I can draw this. Probably, if I just go up like this and around. So this would be wrapped around there, so to speak. Now, if I want to lift this, if I want to make it go up, I have to make this whole wheel and axle kind of turn this way so that it will wind up the red line and lift the object up. And so to do that, I need to have another cord wrapped around the outside, and I need to pull down on this side. So this would be my effort force, and it's wrapped sort of around the outside, pulling up. And my load force is the force over here, which is really the force of gravity causing this weight, right? Okay, now, if you look at the diameters of these wheels, or I guess we can say the radiuses of the wheels. Let's take the center. Okay, I'm going to erase my arrow up here that I drew. And we're going to look at the center. So if I just take this distance from here to here, that's the radius, the small radius. It's the radius of the load, right? The radius of the wheel that the load is wound up on, or the axle in this case. The middle part is the axle, the outer part is called the wheel. But if I take the radius of the big wheel, then it's sort of, there's the radius of the small axle. Here's the radius of the big wheel. That would be the radius of the effort. And so you can see what happens. The radius effort is bigger than the load, or sorry, the effort radius, the length or radius of that wheel is bigger than the radius for the load. So I'm using a larger distance, which means that my effort force can be smaller than my load force. So I'm trading force for distance. Of course, when you pull this around, if you're wrapping around the outer wheel, guess what? You would have to wrap far more string around the outer wheel to get the inner wheel to turn the same amount. So what you would be doing is you'd be pulling out a lot more string, and you would end up with a much greater distance. So this is a trade between distance and force. Smaller force can be obtained by using a larger effort distance with the larger diameter wheel. Okay, that's the wheel and axle. Now, another one you can do, which is similar to the wheel and axle, is you can take a large wheel, but this time you can, all around the outside, you can put what we call notches and make it like a gear. And if we put all these notches on the outside of this wheel, then I take a smaller wheel, which has notches also. Well, guess what happens? If I force this wheel to turn this way, well, then it will cause the blue wheel to catch with the teeth and turn this way. Now, let's again look at how far the distances would be involved. The distance of one turn for the big black wheel is 2 pi times the radius of the black wheel, right? That's the circumference, 2 pi r, once around the wheel. But of course, this little guy here, this blue wheel, he's got 2 pi, but look, his r is much smaller. So he has a smaller circumference. So the larger distance is with the big wheel. And the smaller distance is with the blue wheel. So there again would be a trade-off of wheels. Now, if we use effort wheel, let's say the big one is the effort wheel. This is the wheel that we're turning on the purpose, and this little blue wheel is the load wheel. That's the one where the load is actually on. Then what happens is that we can divide up this circumference right here by the number of teeth. The number of teeth would tell us how far around it is, and the same for around this one. And so for the gears, we can figure out the IMA by counting the number of gears. So the IMA, the ideal mechanical advantage for these gears, would be the number of teeth on the effort gear, number of teeth on the effort gear divided by the number of teeth on the load gear. So N is number of teeth. Okay. And I just realized that we didn't mention the IMA for the wheel and axle. We just jumped right ahead after we talked about it. So we can figure out the IMA for the wheel and axle as well. And the IMA for a wheel and axle can be calculated by looking at the different radiuses, these two guys. And if we take the effort radius, the effort distance, or radius of the effort wheel, and divide it by the radius of the axle of the load, we can get the IMA equals that. So I have to kind of write that down somewhere. IMA for a wheel and axle is the effort radius wheel over the axle radius of the load, and the IMA for a gear can be found by counting the number of teeth on each one. So the number of teeth in the effort wheel or gear divided by the number of teeth in the load gear. This is a lot like a bicycle, isn't it? When you do a bicycle, the pedal has a gear that's usually bigger, and the gears on the back wheel are smaller. So this is like the gear underneath your pedal that the chain is attached to. In fact, if I draw it this way, instead of using teeth that interact, a bicycle is a little bit different, but it works out the same. They use teeth gears, and then they put a chain around, and the chain hooks into the gears, into the teeth. So that's the same effect. So this would be the effort gear that you're pedaling, you're turning the pedals and pumping here, and this blue one is the load which is attached to the back wheel, causing it to turn. And the IMA is all about the number of teeth, so you'll want to write this down somewhere. And the last thing that is related to a lever is the pulley. All right, so we have the wheel and axle, we have the gear, there's the gear, and lastly we'll talk about a pulley. A pulley can do a couple of things. In the simplest situation, if you have a ceiling and you put this thing and you attach a pulley, the pulley is just a little wheel on an axle, and you can put a rope around it. And you could take an object like this, and you could pull on the rope on this end, and you could pull it around, and the wheel would cause this object to go up. In this particular situation, all it really does is change the direction of your force. Change direction of force. It doesn't give you any advantage. In fact, it probably is a slight disadvantage because there would be some friction in the wheel and you would lose a little bit. All right? But you can use pulleys to actually make an advantage. So let's try and see if we can figure out how we would do that. Let's take a different arrangement. Let's take a pulley. Let's say you wanted to lift something, and so what you did is you had a floor here, and then down below was a lower floor. And so you put a hook here, and you put a pulley down here on the bottom. This pulley isn't attached to anything. You just sort of have the pulley kind of held by the rope like this. Okay? And you want it to pull up like this. Now, if you hang from the pulley a mass, what would happen if you pulled up on that green rope? Well, you would cause this mass to go up, and the pulley would rise up. Now, notice what you've done with this arrangement. You're pulling on a rope here, so you're creating what we call tension in the rope, which is like force in the rope. But this tension is in the entire rope. If you pull on this end, the end over here also has the same tension. And since ropes can only pull, you can't push with a rope. If you ever try to push with a rope, it doesn't work. Pulling on this end of the rope creates a tension that also pulls up on this end of the rope. So we have created two lifting ropes. Two lifting ropes instead of just one by using the pulley. And that means that we have, in effect, we can almost reduce our effort force by 2, cut it in half. Now, of course, you have to pull a lot more rope in order to get the same distance. You might raise this pulley from here to here, but the amount of rope you would have to pull would end up being a piece of rope that was probably close to double what you actually moved, the mass. So you see, your mass would go up a short distance, but the rope that you would pull out would be a bigger distance, and there's your trade-off again for force and distance. So you get half the force, but you get double the length of rope. And if you make a pulley, any kind of wheel with a rope, you can experiment with this and you can see. And if I get a chance, I'll maybe try to make a video for you so that you can actually see how that would work. Now, there's lots of different arrangements of pulleys. So you can get all kinds of cool sort of things. Let's take a look at another situation. Let's take a pulley where I have a ceiling and I attach a pulley to the ceiling. So there's the first pulley, and it spins around like that, but it can't move. It's attached to the ceiling. And then down below, I have another pulley that can move. It's just kind of there. It's not attached to anything. Okay? But I attach that pulley to a mass that's hanging off of it. So that's what I want to lift. So then I get a rope, and I wrap the rope up around the first pulley like this, down around the second pulley, like this, and up here, and I just sort of tie it off to this support, so it's stuck. Now when I pull down on this rope, this is a down pull. See this guy on this side? He's a pulling down, so he's not lifting, is he? You can't lift by pulling down. But I have created tension, and the tension will be the same in all the ropes. So the tension will cause lifting here and here, and I will get 2 lifting ropes out of this arrangement. So it kind of looks like it's the same as the other one. The difference is here, I can stand down here on the bottom and lift my object up, whereas on the other picture, I had to stand up here above it and lift the object up. So it depends on where you want to go. Now, you can also do this. Let's take a thing here. Let's put a couple of pulleys here. Let's put one pulley here and another pulley here. And then down below, we'll have one pulley here and another pulley here. And we'll attach our mast to the bottom pulley, like this. There's our weight. Now, when we run our rope, I'll have to make sure I do this the right way. We're going to go up, like this. Down, like this. Around, like this. Around, like this. Around the other pulley, and finally tie off right there. That's a lot of loops. Now if I pull here, this pulley is down. That's not lifting. It's pulling down, but it is creating tension. And the tension it creates will cause pulling in all the other ropes. So there will be pulling up here, pulling up here, pulling up here, and pulling up here. I've created 4 pulling up ropes by doing this. And guess what I've done then? What I effectively do will reduce my effort force by 1/4. I'd be able to lift this object and only pull with 1/4 of its right weight. So the different combinations of pulleys, you'd have to probably connect these pulleys together with a bar or something to make that work. But the beautiful thing about pulleys is you can make all kinds of combinations, 4 pulleys, 6 pulleys, 8 pulleys, and you can use them to create lots and lots of pulling up ropes, which allow your object to be lifted with hardly any effort force at all. The trade-off is, with this pulley system, you have to pull an awful lot of rope. You have to pull out 4 times as much rope as you would if you were just lifting this up with one rope from the bottom. 4 times as much rope. So there's the extra distance that you're trading for. Okay, well the actual mechanical advantage is the ratio of forces for all of these, but the ideal mechanical advantage, since we don't have arms on the pulley so much, can be simply figured out by counting the number of supporting strands. Count the number of supporting ropes, or pulling up ropes. Supporting, I'm going to put in brackets, pulling up ropes, but not pulling down ropes. That's the trick. Like over here, there are 4, but see this one on the far side is not a pulling up rope, unless you rig it so that you were up on top and you were pulling up with that rope as well, like in the other example. And so in this case, the example is 4. The IMA is equal to 4 because there are 4 pulling up ropes, which means that you would be able to lift 4 times as much load with the same force. Or a better way of thinking of that would be that it would require only 1/4 of the effort to lift an object, 1/4 of the load force. Okay, and that is the pulley and the wheel. So just to summarize, right, we have the lever, we have the wheel and axle, and we have the gear, and we have the pulley. And what we'll do is we'll show you how to figure out the IMA and the AMA for each one, just to kind of remember. So for the lever, let's put AMA first and put IMA over here. So we'll make kind of an upside down chart. All right? Like that. Like that. Well, the AMA is always the same. The actual mechanical advantage is always the load force divided by the effort force. Okay? Load force divided by the effort force. For the same for the wheel and axle, because these are just simply the forces that you're pulling on the gear or the wheel or the pulley or the lever with. So that doesn't change. That's easy. Load force divided by the effort force. But for the lever, we found that if I take the effort arm length and divide it by the load arm length, I can get the ideal mechanical advantage. The lever. For the wheel and axle, it's the ratio again of the radius of the effort wheel and the radius of the load axle. So it looks the same, but you have to remember it's slightly different. It's a slightly different number. This is all about the load arms. The load, well, actually not just the load and effort arms. So let me write here that this one is arm lengths, right? Which is the distances from the fulcrum of the load and the effort. Whereas this one is the radius or the radii of the wheel and the axle. So it's the same letters, but it means something slightly different. For a gear, we said that you could just simply do the ratio of the number of teeth. Number of teeth on the effort wheel or gear and the number of teeth on the load gear. So this is number of teeth. Number of teeth. And for the last one, the pulley, it's simply to count the number of lifting strands. Lifting ropes or lifting strands. Supporting strands. And that's how you calculate the IMA for each one of these little fellows here. And so what I'll do in after the video, I will give you a little assignment to practice figuring out the AMA and the IMA for a bunch of simple machines that fall into this, which is all called the lever family, the family of the lever. And that's as far as we'll go today.